hello. I'd like to welcome you to the first part of the lecture from today. And today's topic will be the porous silicon carbide, or in particular, the preparation of porous silicon carbide from monocrystalline wafers and its applications. And in the beginning of the lecture, I would like to cover a few basic topics about semiconductor photoelectrochemistry, because this is the method how porous silicon carbide is produced here at our institute. And in the beginning, as I already said, I would like to cover a few basics. In case you already know them, please you can skip it. If not, hopefully I can explain you the basics such that you have an understanding when we will talk about the specific material, namely porous silicon carbide. And this is not an exhaustive treatment of the basics, just an overview that you have an idea of what I'm talking about. And I would say now let's have a start. So we will cover the principles, or let's say some basics of semiconductor electrochemistry. So first point is we would like to start with, or I would like to start with the electrolyte semiconductor junction. So electrolyte semiconductor junction. So what is it? It's the interface between a semiconductor and an electrolyte solution. Interface between semiconductor and electrolyte solution. So an electrolyte, it's basically just a conductive liquid. Simple examples are water with salt dissolved in it. The salt forms positive and negative ions, meaning that the solution is conductive for electricity. So let me give a schematic, or let's develop a schematic of this junction. And first, I would like to address the semiconductor. So let's repeat some basic properties of semiconductors. And therefore, let's begin. We have, let's say, an energy axis, where E is the energy. Then we have spatial coordinate, let's denote it as X. We have the conduction band H and the valence band H, CB for conduction band, VB for valence band, and in between those two no energy state is allowed, meaning the semiconductor, like the most prominent example being silicon, is also made up of electrons, and these electrons cannot occupy, or some energy states are not possible to be occupied by electrons. Let's say if I pick an electron from the compound or from the semiconductor, in between conduction band H and valence band H, you cannot find an electron, because by physics it's not allowed that an electron can occupy an energy level in between here. And in the conduction band and in the valence band, or let's say energy states for the electrons are allowed. They are still discrete states, but the gaps between those states, they're very tiny, so therefore I draw it here like this, but always remember it's not a continuum. It's there are many electronic states being allowed to be occupied by an electron, but they are still discrete, so it's not a continuum. I just want to indicate, okay, these are areas where you find a lot of allowed states for an electron, or that an electron can occupy. So in between the valence band and the conduction band, we have the Fermi level. Let's say let's denote it as EF, which is approximately the electrochemical potential of the electron. So first, let's start. What is the Fermi level? One can define it as the Fermi level. One can identify it or define it as the probability to find an electron E minus is 1/2 at 0 Kelvin. And the difference between the Fermi level and the electrochemical potential is that the electrochemical potential also takes temperature effects into account. So let me explain this a bit. So the distribution of electrons is described by the Fermi-Direct statistics. Let's say here we have a probability to find an electron of 1, here of 0, and one can draw this distribution. This would be at temperatures higher than 0 Kelvin. One can draw this distribution, so there is this probability to find an electron in the conduction band at temperatures higher than 0 Kelvin. At 0 Kelvin, this would be a rectangular block. So no electrons are in the conduction band, or no free electrons. And this turning point here of the distribution is can be identified as the Fermi level. But if one wants to be very accurate, that one has to say this is the electrochemical potential of the electron, because per definition the Fermi level is independent of temperature. But if you are very correct, then this turning point is a function of the temperature. So let's write this down, the electrochemical potential of the electron. So it is approximately the Fermi energy, but the electrochemical potential, but mu tilde, mu e tilde takes also temperature into account. Okay, so far so good. Did I forget something? Here, no. Okay, and this is now the intrinsic case. So what does this plot mean? Let's say you have a semiconductor, and the semiconductor is characterized by its band gap, the difference between valence band edge and conduction band edge. And let's say at finite temperatures, or at let's say at room temperature, some of the electrons in the valence band can be thermally excited to the conduction band. And in the conduction band, the electrons, they can move freely in such that the semiconductor becomes conductive. Now this property of this thermal excitation is exploited if one introduces here discrete states that occupy electrons. The population of electrons here will change, because they can thermally, at room temperature, they are already thermally excited to the allowed states in the conduction band. Hence, the Fermi distribution is changed, such as this. Okay, I'm drawing, it's not completely good, but now for the doped case, the electrochemical potential would be here. One can put this into equation. So for the undoped case, let's say this case here, the amount Ni of electrons in the conduction band, and I denotes here intrinsic case, is equal to the density of states and some exponential kT minus mu. Mu tilde electron intrinsic. Intrinsic means for the undoped case. Okay, so physically, as we've already said, you have a certain band, certain difference between the allowed states. So here's just half, okay, but you have the difference between the electrochemical potential and the conduction band edge, and this barrier is related to the concentration of electrons in the conduction band. So now let's make also a drawing. And here in this region we have at temperatures higher than 0 Kelvin, probability higher than 0 to find an electron. However, we can write an equation for the intrinsic case, for the undoped case. We could write the same equation for the doped case, meaning that mu changes here, and this number would be higher. And if one equates these two, or if one combines these two equations, one can arrive at an expression that describes the position of the electrochemical potential at this energy axis. So let's write it down. Hopefully you see it. So mu tilde E, now this is now for the doped case, is related to mu tilde E I for the intrinsic case. If one has not inserted these states here in the semiconductor, and kT ln of n divided by mi. So intuitively it's now clear one can shift the electrochemical potential in this diagram by introducing these states here, and therefore you have higher number here, and this higher number here of electrons in the conduction band is related to a shift upwards of the electrochemical potential. So practically, yeah, what would be such dopant elements would be, let's say, nitrogen for silicon. So the nitrogen ions or atoms, they can donate electrons to the conduction band. I will not cover here, and this is now called N-type doping. N-type doping meaning okay, you have a conductivity by electrons, by free electrons in the conduction band. You could also do P doping, then you would insert empty states here, and electrons from the valence band would be excited to these empty states here, and such that the remaining holes contributes to the conductivity of the semiconductor. But in this course or in this lecture, we will just consider N-type doping. So now we have covered the semiconductor. Now let's move to the electrolyte. So in the electrolyte we have a redox couple. In the electrolyte we have a redox couple. So what is the redox couple? Let me first give you a practical example, or before becoming abstract, let's give a specific example. it would be iron 2 plus and iron 3 plus ions. They form a redox couple. And they are in the solution, they are in equilibrium. So if I have a solution, let's say water, I dissolve iron 2 and iron 3 salts in the solution, then there is an equilibrium in the solution between the iron 3 plus and iron 2 plus ions. And one interpretation is they always switch the states. So iron, oh, that's wrong here, sorry. Iron 3 plus ion accepts an electron, becomes iron 2. Iron 2 releases electron, becomes iron 3. But there are no free electrons in an electrolyte solution like in the semiconductor, and that's why that's also one reason why we're talking about this, because let's say in the semiconductor we have said we have the free electrons, in our case in the conduction band, that they can move freely. But in the end we are interested in the question what happens if we bring the semiconductor and the electrolyte solution together, and what happens then, but because how to describe it, because in the solution we do not have those free electrons. So first question is what would be an interpretation of this, or how can one think of this? Let's say we have a metal electrode, or just a piece of metal, and it's surrounded by the electrolyte. And so it is a beaker, and then we have the iron 2 plus ions. They donate an electron in the metal. The electron can move and donates it to iron 3 plus, and this becomes iron 2 plus again. And that's one way of looking at it. So there is an equilibrium, but the electron transfer is established via some material where that can transmit the electrons. But that's my interpretation of it. So, this is one practical example. I hope you got some sense of what I mean. The very abstract definition, however, would be that you have some species A in the solution plus an electron is in equilibrium with A minus. And it's basically the same as we were just the same stuff we were just talking about, but I've just replaced the specific example with an abstract definition. However, we have for the semiconductor we have covered the electrochemical potential, and in particular the electrochemical potential of the electron. And the electrochemical potential is in this case some sort of parameter that describes energy distribution, but also physical interpretation would be that it is the amount of energy that is required to remove an electron from the semiconductor. Because let's say I'm here, and this is some parameter that describes how much energy is needed to excite an electron from this state here into vacuum, which is equivalent to removing it from the material. Same is true for A. The electrochemical potential describes this for A, for the electron we just had, and also for A minus. So one can write nu tilde of A plus nu tilde of the electron equals mu tilde of A minus. Now, why is this true? One can derive this, but let's say one interpretation is, let's say we are here in equilibrium in the solution, and this happens constantly, but for the external observer, no change is there. Also the energy does not change. Why should it? And let's say if in equilibrium this A plus E minus is lost and becomes A minus, then the electrochemical potential here, let's say, is gained because it's lost, and is gained here, and here it's lost because this one is gained. So hopefully I could explain this quite good. Let's say it's really just because we're in equilibrium, because let's say if A minus loses an electron, then you have a change in electrochemical potential. And this change must be equal to the electrochemical potential of A plus the electrochemical potential of the electron, because this is created and it's constantly happening. Yeah. So in equilibrium, therefore, this is true. And for what does it mean for us? Why is this kind of interesting for us? It's because if one brings this to this side, one can find, let's say, an abstract definition of the electrochemical potential of the electron for the solution, even though there are no free electrons in the solution. And not very surprisingly, this electrochemical potential in the solution, it's related to intrinsic electrochemical potential, or intrinsic, here more meaning for standard conditions. So the electrochemists, they have defined standard conditions for a certain pressure and concentration, and the concentration at standard conditions for every species would be 1 mole. But however, let's continue here, then maybe this will become more clear. However, now let me finish here, sorry. I think this should be correct. I hope so. Yeah. So what we have here now is that we have found an expression for the electrochemical potential also in the electrolyte. And it's the same as in the semiconductor. In the semiconductor, the position of the electrochemical potential was determined or adjusted by doping. And here it's adjusted, not surprisingly I think, by the composition of the electrolyte solution, meaning of how much A minus, or for in a specific example, iron 2 plus or iron 3 plus you have in the solution. And for standard conditions, these two guys, they would be equal to 1. This would become 0, and you have the electrochemical potential defined for the intrinsic case. So now we can add to our drawing here some new elements. Here we still are in the semiconductor. You can add here now the electrolyte. So we have now derived that in the electrolyte we also have this mu tilde of E of the electron. Let's say one can draw it here. Mu tilde of E. And mu tilde is determined by A and A minus. And actually the energy distribution of A and A minus, the energy distributions are 2 Gaussians, because also the solvent, like water or so, has and also thermal movement has an impact on the energy distribution. So it's not just single line, but a distribution. So this is the energy distribution of the A and A minus species, and the intersection between the 2 Gaussians determines the electrochemical potential. So hopefully this is somehow clear to you, or at least my hope was here to give you an idea of what I'm talking about. So maybe, so it's 2 points one could denote, I think. So we can define identify the electrochemical potential of the electron U tilde in both semiconductor and electrolyte. And what do we have also now, theoretically, framework for charge transfer at the junction. However, in the next sub-lecture we will treat the current voltage characteristic when we bring the semiconductor and the electrolyte together. And here from this lecture basically is the main things are to remember that you have a semiconductor. In the semiconductor you can identify the Fermi level and the electrochemical potential of the electron. You also have the electrochemical potential of the electron in the electrolyte solution, and when you bring them together, they will form an equilibrium. And why it is here, one could also say that you have a Fermi level in the electrolyte solution, but the ions in the electrolyte solutions, they do not follow the Fermi-Dirac statistics. So some theoreticians say, okay, you can also assign a Fermi level to the solution, but I think there is an agreement that you are very safe when you're talking about the electrochemical potential here and the electrochemical potential here. Yeah. However, also maybe some literature tips. There are Wikipedia articles in the German Wikipedia about the chemical potential, and I think this is a very good article because I also contributed to it. So if you're curious about the topic, just have a look there, or write an email, or maybe even give me a phone call if you want to know more about this topic.